Welcome to our first lesson of heat transfer. First of all, we want to define heat transfer. It's a form of energy that is transferred from one point in space to another because of a temperature difference. So here I've sketched two systems, one at temperature T1 and the other at temperature T2. And these two systems interact with each other. The temperature T1 is larger than temperature T2. So we have a transfer of thermal energy, of heat, from T1 to T2. We usually indicate heat with a capital Q. Now, I would like to give you some suggestions for books on heat transfer. The first one is the book by Kengel, Heat Transfer, A Practical Approach, published by McGraw-Hill. The other one is Bergman, Incropera et al., Fundamentals of Heat and Mass Transfer, published by John Wiley and Sons. This is the book I use as an undergraduate. And then this book I also used when I was instead a master's student. This is slightly more advanced. It's Convective Heat and Mass Transfer by Case, Crawford and Weingart, published also by McGraw-Hill. So while thermodynamics is the science concerned with the amount of heat transfer between equilibrium systems, we're now interested in heat transfer because we're interested in the rate of transfer of thermal energy. So, for example, we're interested in how long and how fast this heat transfer occurs. We're also interested in how this happens. So heat transfer can have different modes of transfer, so it can happen by conduction, by convection, or by radiation. And in general, we are concerned with systems that are not in equilibrium. We'll be using two fundamental laws of physics. The first one is the first law of thermodynamics, that is concerned with the conservation of energy, and also with the second law of thermodynamics that can have different forms. And in particular, we are interested in the form that says that Q, heat, flows in the direction of a decrease in temperature. And the difference in temperature, delta T, is the driving force for heat transfer. Or more specifically, heat transfer occurs because we have a temperature gradient, indicated in this form. So, if there is no temperature difference, there is no temperature gradient, then there is no heat transfer. Where do we see heat transfer? Well, the first clear example is obviously the sun. So by radiation, we received energy from the sun. Human body is, of course, a system that has a lot of heat transfer occurring. We have in our houses, we have a lot of heating systems, electrical appliances, many of them involve heat transfer. We have heat transfer in power plants, computers, and geophysical systems like the Earth itself, of course, has a lot of heat transfer involved. In engineering heat transfer, we are concerned with two kinds of problems. The first problems are called rating problems, and the second kind of problems are called sizing problems. In rating problems, we are given the temperature difference or temperature gradient, we're given the size of the system or systems, and we want to find the heat transferred. Instead, in sizing problems, we are given the heat transfer, we are given the temperature gradient, and we want to find the size of the system. What kind of methodology we can adopt to solve heat transfer engineering problems? We can have an experimental approach, so we go in the lab and we carry out a real experiment. So this is a real physical system. But often these experiments are very expensive, they take a long time, and they're very hard to conduct. Often in the lab, we scale down the problem, so we do experiment on a system that's smaller than the real one. The other approach is the analytical, theoretical, or even the numerical approach. These approaches are faster, but often rely on hypotheses, on approximations. So the system that we actually solve theoretically or numerically is often a very simplified version of the real one, and the model often can be non-realistic. So the best way to tackle an engineering problem in heat transfer is actually to combine these two methodologies. About the modeling approach, we have to follow a few steps. First of all, we define the variables of our system. So for example, the size, the geometry, the temperature, we define the pressure, or the dimensions in so this is the first important step. Once we have done that, we can think and use some assumptions, some approximations. So in this way, we can actually simplify the problem and still make it realistic. Then we use a physical law. So we talked about the first law of thermodynamics, conserves the energy, or also we use often the conservation of mass. Then we express the physical law in mathematical form, and this procedure leads us to differential equations that describe the system. Once we have a differential equation, in some cases we can solve it analytically, so we have a closed form solution that's ready to use. But often we have to rely to computer codes, so we solve it numerically. And again, a good approach is to use both approaches and compare the solution. What we want to do now is to define some useful quantities and concepts. So the total energy of the system is of course important, indicated by a capital E. Instead, if you use E small case, is the total energy divided by the volume, so per unit volume. The unit of E is J, joules. If you have small e, small case e, instead is joule divided by meter cubed. The total energy can take different forms, like thermal energy, electrical energy, kinetic energy, potential energy, magnetic energy, chemical energy, nuclear energy, and so on. In this course, we focus, of course, on thermal energy, and specifically on how it is transferred. It is, of course, also important to define the internal energy, indicated by capital U, or if you want to, the internal energy per unit volume, we have capital U divided by the volume, and then we have a small case u. The internal energy is the energy related to the microscopic activity of the system. We also want to define an ideal gas. An ideal gas is a gas that obeys this law, and usually if you have a gas at low pressure, that's a very good approximation. The ideal gas law says that the pressure is equal to the product of the density, the gas constant, and the absolute temperature. Usually in this course, we'll be adopting the approximation of ideal gas. We define then a specific heat that is defined as the energy required to raise the unit mass by a temperature of 1 degree. We can have a specific heat at constant pressure, indicated by C subscript P, or a constant volume. So we have C subscript C. For an ideal gas, Cp is equal to Cv plus R. The unit of a specific heat are joules divided by kilograms degree Celsius. But for specific heat, and actually all the problems in conduction and convection, we can also use joules divided by kilograms degree Kelvin, because the scale of temperature of degree Celsius is linearly related to the scale of temperature in Kelvin. So a delta C degree Celsius is equal to a delta T in degree Kelvin. The change of internal energy, delta U, is equal to a mass, the average specific heat constant volume, and the change in temperature. In the specific case where we have an incompressible substance, so a substance where the density is constant, for example in liquids and solids, this is usually a very good approximation, the CV is equal to Cp. We can now define a heat transfer rate. We define Q, capital Q, as the energy transferred in joules. If you add a dot on top of Q, then we have the energy transfer per unit time. That's a heat transfer rate. So that's joules divided by seconds. And the units, of course, corresponds to watts. If we have Q dot as a function of time, we can integrate over delta T, that's the interval in time. So we integrate from 0 to delta T Q dot in dt, and we obtain the energy transferred, Q. We also define an heat flux, indicated by small case q dot. That's big Q dot divided by the area. So is the heat transfer rate per unit area. And of course, the units are watts divided by meter squared. We mentioned earlier the first law of thermodynamics. So we can now define it. First law of thermodynamics expresses a conservation of energy. So energy cannot be created nor destroyed, but only changes form. So if you have a system and this system undergoes a sort of change of energy on some form, delta E, and this must be equal to the energy injected into the system, E in, minus the energy that's taken out of the system. So we are written here this in algebraic form. This is in joules. So that's it, the energy change. But we can write the first law of thermodynamics in per unit time. So E in dot minus E out dot must be equal to the derivative of the energy with respect of time. In the steady case, this derivative is obviously 0, so the energy in must be equal to the energy out. In our specific case, in our course of heat transfer, we don't have any mechanical work, so the difference in heat injected into the system and taken out of the system, plus some form of heat generation inside the system, for example, some chemical or nuclear reaction, or some heat generated by Joule's effect in electric circuit, must be equal to the change of thermal energy of the system. What if you have the special case of a closed system? In this kind of system, the mass is fixed, so in the case there's no work. So the heat injected into the system must be equal to the change of internal energy, equal to mCV delta T. And now we can introduce the concept of mass flow rate. M dot, mass flow rate, is equal to the product of rho VAC, where rho is the density of the fluid, V is the mean velocity, and AC is the cross-sectional area. So if you have, for example, the flow through a pipe or a duct. In the case of steady flow system, the mass flow rate enters this formula. So we have the Q dot, the energy transfer, the heat transfer, is equal to m dot mass flow rate times Cp times delta T, and the units are in watts. If you have a steady flow system, then m dot is constant. And we consider the case where there is no work or potential and kinetic energy are negligible. So here I represented the flow through for example, a pipe, and this is our control volume. If we know how much heat we inject into the system, we know m dot, we can find the delta T, the change in temperature. And in this case, of course, the temperature T2 would be larger than the temperature T1 because we have given heat. We've given heat through the boundary of the pipe, and so we have increased the thermal energy of the system. The final concept for today is the concept of first law of thermodynamics, so energy balance across a surface. By definition, a 2D surface has no volume because it has no thickness. So there's no mass associated with the surface, there's no energy. So the energy going in from this side of the surface must be equal to the energy coming out. We see many examples of this in our course. If you have some heat conduction through a wall, and we define our surface as the external surface of the wall, the heat conduction must be equal to the sum of heat convection and heat radiation. The surface energy balance concept is very important because it will allow us to find the boundary condition of our differential system. Okay, that's it for the day. Thank you very much.